A series is a summation of a sequence. And an infinite series can either be convergent or divergent. A convergent series goes to a specific point as the series reaches infinity, while a divergent series will go to positive or negative infinity.
Here is our first summation problem. So, looking at this, what do we know? I think that it is decreasing because as n equals infinity, the terms would seem to decrease as the bottom approaches infinity at a faster rate. It also seems to be positive. Let's see. I think that this is decreasing, discontinuous, and positive.
Alicia, stop. It's not discontinuous, it's continuous, alright?
Oh, so if it's decreasing, continuous, and positive, the integral test must work to solve this.
Welcome to another episode of High IQ Math with your host Akshay and today's magician's assistant Michelle. Today we're going to be solving this summation, the summation of n equals 1 to infinity of 6n squared over n cubed plus 1. Now tell us, Michelle, what test do we need to use to solve this summation?
The integral test.
The integral test. How convenient. So, using the knowledge that we learned about the integral test, let's apply it. What do you think the first step is? Since this is not a proper integral, we must use the limit notation to take that infinity out of the bounds. That means that, that's a b. We must use limit of b going to infinity of the integral of 1 to b of 6n squared over n cubed plus 1, dn. Now let's use u sub to solve the integral. U is n cubed plus 1. Let's find the integrand. As we know, the integral of 1 over u is natural log of u. So a final is 2 times the limit of b going to infinity of the natural log of the absolute value of u evaluated from 1 to infinity. So now we have to plug in these values. So what is the natural log of infinity cubed plus 1? That's infinity, and that is not a value. So since we know that one of the values is going to be infinity, the integral is going to diverge. And since we know that this summation is decreasing, continuous, and positive, we can use the integral test to prove that it diverges.
Okay, we have another series problem. So when trying to see if a series converges or diverges, we have to check one of these tests before we determine if we use these tests. So let's start with the nth term test. I wonder what that tells us. What does it tell us?
Convergence or divergence. The nth term test tells us whether the series converges or diverges.
I thought all the tests did. What is so special about the nth term test?
It's easy to do.
Okay.
So what you do is you find the limit as n goes to infinity of a of n, a sub n. And if a sub n is not equal to 0, then the series diverges. That's correct. But if it is equal to 0, it does not mean that it converges. It could be anything. We just don't know.
Okay, let's take the limit of this series. Okay, what points are here? Okay, thank you, Akshar. Let's take the limit of this series. Wow. See, using what we know about limits, we can see that as n approaches infinity, this 1 really isn't significant. However, the bottom is approaching infinity twice as fast as the top. So the limit is 1/2. That means this series diverges. Going down our list of tests, we see the p-series test. Now we all remember that for p-series, your series has to follow this form. And if p is less than or equal to 1, it diverges. But if p is greater than 1, then it converges. Okay, so now looking at this integral, I don't see that this is in the form 1 over n to the p. So I don't think we can
Wait. Alicia, this is a square root. Give me that thing. This is we can see that this is the same thing as the summation of 1 to infinity of 1 over n to the power 1/2, which fits into the p-series notation.
Wow, thank you.
No problem. Now we can look at this p-value right here. Since the p-value is equal to 1/2 and 1/2 is less than 1, you did, oh, crap. Since we know that the p-value is 1/2 and 1/2 is less than 1, we know that this series diverges.
Alright, so here we have a problem, a series from n equals 0 to infinity, a summation of 3 to the n minus 2 to the n all over 6 to the n. So you can see the tests here that we've used so far and that we're yet to use. So I'd like you to just take a moment to pause the video and consider which test you should use. Okay, so I'm assuming you paused the video and I guess you haven't found the solution, so we're gonna go over this. So first, well, I looked at the nth term test, and you should too. You should see that 6 to the n is probably like a lot bigger than 3 to the n. I mean, at least to me, that's kind of intuitive. So then we're gonna assume that this series converges. Okay, so one thing that's usually really helpful is to try to separate the parts of the function here. So here we have a thing that's like a minus b over c, and you can kind of like separate that into a over c minus b over c. And that's what Oxford is going to do. He says he sees 3 to the n over 6 to the n minus 2 to the n over 6 to the n. And all he did was take this fraction apart and but now he's going to evaluate these fractions. And what we're doing here is it's basically this is basically you can take the entire fraction because it's a to the n over b to the n. You take the entire thing as a over b to the n. So really it should really be 1 to the n over 2 to the n and 1 to the n over 3 to the n, but we know that n 1 to the n is just 1, so that's why after 1 over 2 to the n. And now what we're gonna do is we're just gonna break up the summation into 2 parts. Alright, this is a geometric series. And also, just pause for a moment. Tell me what the first term is. Because we don't want to make the common mistake thinking the first term is half or 1/4. Notice that it goes from n equals 0 to infinity. So plug in 0, you get 1 over 2 to the 0 is 1. And the same on this side. So you want to use the formula for a geometric series, which is a over 1 minus r, where a is the first term and r is the common ratio of the geometric series. And so the common ratio here is half, clearly because you have like 1/2, 1/4, 1/8, and here it's 1/3. And the first term for both of them is 1. So we're going to plug it into our formula. We have a1 over 1 minus r. So I think Akshay made a little error there. It's 1 over 1 minus 1/2. Yes, and what is the second one? It is 1 over 1 minus 1/3. And we just evaluate these. We get 2 for the first fraction. And the second fraction is 3/2. And we evaluate this and we get 1/2. So our original series is really just this series, which is convergent to 1/2. Hey guys, so today we have, well, all these problems are today. Right now we have a series from n equals 1 to infinity of 2 over 4 n squared minus 1. And honestly, what you gotta think about in these scenarios is, what does this function look like? And to me, well, we gotta try a few things out. So, I mean, I'm gonna try the geometric series.
Wait. This is what they call it. High IQ math is oddshot, okay? This is obviously a partial fraction, okay? What you gotta do is you gotta decompose the fraction. So you get the summation of n equals 1 to infinity of 1 over 2n minus 1 minus 1 over 2n plus 1. You think you can get it from here, Harley?
I think you should just take the regs.
Okay, fine. This summation gives you the partial sum of 1 over 1 minus 1 over 3. Then you get 1 over 3 minus 1 over 5. And you can see that these terms will cancel out, right? And since it's a pattern, it'll continue for infinity. So in the nth term of this sequence is going to be 1 over 2n minus 1 minus 1 over 2n plus 1. Right? And since we know that this term is going to cancel with the term before it, we can get rid of all these terms in between, and what you'll be left with is 1 minus 1 over 2n plus 1.
And so the answer is 1.
Wait, we're not done yet, Harley, you goofball. We have to take the limit as n approaches infinity of this function. And since we know that the n is in the denominator,
You're so slow. The answer is 1.
and the n goes to infinity, this term is going to equal a big 0. And it's
So
going
it's
to cancel
0.
out. So the answer is actually 1.
Wait, it's 1! No. Okay, so here we have what is quite clearly an alternating series. You have -1 to the n plus 1 or -1 to the n. And here in this case, it's -1 to the n plus 1. So we're going to try to use the test. So for the alternating series, we have two conditions, and that's the non-alternating part of the series is strictly decreasing, and that the nth term limit is 0. So to me at least, the nth term is clearly 0 because like 1 over really big numbers 0. So we're just trying to prove that this function, the non-alternating part, is decreasing. So which is the alternating part? Okay, I hope you pause for a moment there. The alternating part is going to be -1 to the n plus 1 because it's going to be like -1, 1, -1. So we just had to look at this and see if this is decreasing. So we would write 1 over n factorial, and the next term would be 1 over n plus 1 factorial, right? And yeah, so this difference has to be positive, which means it's positively decreasing every time, which means it's getting smaller every time. So if this is positive, that means it's decreasing every time. I hope you can see that. So what we're going to do is we're going to multiply the top and bottom of this fraction by n plus 1. So we get n plus 1 over n plus 1 factorial minus 1 over n plus 1 factorial. And now we're going to, they have a common denominator, so we just have n over n plus 1 factorial. And this is the difference between the positive difference between any two successive terms, which means that this is how much it's getting smaller by on every term. So therefore, it is decreasing, and so it passes our alternating series test for convergence. So this series converges.
Hi guys, welcome to Medium IQ Math with Akshat. It's medium IQ because today we're doing the direct comparison test, which does not need that much IQ. We have this infinite series here from 0 to infinity of 1 over 2n plus 1. So if we look at a ever-growing list of tests over here, we can see that with the nth term test, it'll go as n goes to infinity. This series will become the limit will go to 0. So it's inconclusive, and it doesn't fit the form for p series and geometric series because you have this plus 1. But then we can go down here to use this direct comparison test. So when could we use the direct comparison test? The DCT is most effective when you have functions with a scalar translation, like 1 or any other value. You just need to find another series which is either greater than or less than this function. So today I'm going to compare this to 1 over 2 to the power n. This function is always going to be greater than this function because the denominator in 2n is always going to be less than the... Thank you, Harley. Because the denominator here will always be less than the denominator in 2n plus 1. So now we can find the infinite series of 1 over 2n. See, this is a way easier series to find the convergence or divergence itself because it fits directly into the geometric series test.
I would just like to confirm that when Akshay says 1 over 2n, he means 1 over 2 to the n.
Yes, very cool. Now, using the geometric series test, since this R value is less than 1, we know that this series will converge. The value it converges to is not important. Now since we know that 0 is less than 1 over 2n plus 1, and that is less than 1 over 2 to the n, and we know that this will converge, we can prove that the smaller function will also converge with DCT. Thank you. Hi guys, welcome to Medium IQ Math with Akshay. Today, we're going to be solving this infinite series from 1 to infinity of the square root of n over n squared plus 1. Let's look at our tests and see what we can use. First, we apply the nth term test as always. Using the nth term test, we get that this series will go to 0, so it's inconclusive. It doesn't fit into the p series or geometric series forms easily, and it's not alternating, and it's not telescoping. So we must go to these tests. Since we have an exponent on the top and the bottom, I think that we should go with the limit comparison test. The limit comparison test, in the limit comparison test, you have to create another series, Bn, which you will divide an by, and then you will get a value c. C has to be finite and positive, so you must remember this. If c is infinity, or if c is a negative value, the limit comparison test is inconclusive, and you must either find a new limit, or you must use a different test. And Bn must be greater than 0. Okay, so let's find a good Bn to use with this function. Since this is going to be the An, the Bn has to be able to conveniently get rid of some of this messy stuff we don't want. So the Bn, we can make the Bn like, let's say, square root of n over like n squared. Okay? Now let's divide these two terms. So an is going to be square root of n over n squared plus 1. And you have to multiply by the reciprocal of this function to divide. You get n squared over square root of n. Right? And you have to take the limit as n goes to infinity. These square root n's will cancel out, and you're going to be left with n squared over n squared plus 1. Now, as you take the limit of this function, you get that the limit as n goes to infinity of n squared over n squared plus 1 equals 1. This is a constant value, and as you can tell, it's both finite and positive. Therefore, the series will converge by the limit comparison test. Thank you. Hi guys, and welcome back to High IQ Math with Akshat. Today we're going to be looking at the infinite series from n equals 0 to infinity of n squared times 2 to the power of n plus 1 all over 3 to the n. So first, as always, let's look at the nth term test. With the nth term test, we can plug in the limit as n goes to infinity, and you could solve this, but like with the L'Hopital's and stuff. But take my word for it, it'll be 0. It's inconclusive. Okay, don't even bother. P-series and geometric doesn't fit into any of those forms. Alternating series, telescoping, you're goofy if you see an alternating series in here. Okay. And now we can look at the direct comparison and limit comparison, which might work, but the ratio test is going to be the most efficient for this type of series because we have n in the exponent, and we have many n terms. So what we have to do for the ratio test is we have to create a new series, or we have to create a new function bn, which is the n plus 1th term of this series. That's going to be n plus 1 squared times 2 to the power of n plus 2 all over 3 to the power of n plus 2.
Yeah, so what Akshay did here was he just plugged in n plus 1 and replaced where we had an n, so what he actually meant was n plus 1 here.
Yeah, that's what I meant.
Yeah, just trying to check if you're paying attention.
That was the test. Okay, so now we have to take the limit of n going to infinity of, so we have to take this function n plus 1 squared times 2 to the power of n plus 2 over 3 to the power of n plus 1. We have to multiply that times 3 to the power of n over n squared times 2 to the power of n plus 1. Now, we can start canceling some terms out. So 3 to the power of n plus 1 is actually just 3n times 3. 3n and 3n cancel out. And we can do that for all of these terms, which I'm sure you can do. In fact, you can pause the video and try this for yourself. And then, at the end, you'll get the limit as n goes to infinity. That's an 8. Look at my magician's assistant, Holly, coming over here to help out. And we get the limit as n goes to infinity of 2 to the power of n plus 1 whole squared over 3n squared. Now, what we can do is plug in these n terms, right? And what we'll get is, what that will evaluate to is 2/3. Now, we can look back at the ratio test, and we can look back at the ratio test and see that if the n plus 1th term of a over the nth term of a is less than 1, then the series will converge. And we have a value 2/3 here. And as Harley can tell you, 2/3 is actually less than 8.
And what I can also tell you is that when Akshay multiplied by the reciprocal here, that's exactly what he was doing. He was dividing a of n plus 1 by a of n. And didn't really show that, but it's really just division by the reciprocal of this.
Good job, Harley.
Thank you.
So, now we can prove that this series converges by the ratio test. Thank you. Hey guys, and welcome to another episode of High IQ Math with Akshat, Home Edition. Today we're going to be finding the interval of convergence for this summation. The infinite series of n equals 0 to infinity of negative 1 to the nth power times x to the power of 2n plus 1 over 2n plus 1 factorial. So to find the interval of convergence or the radius of convergence of any series, we must use the ratio test. The ratio test, as defined in the previous video, you must divide the n plus 1th term by the nth term. So the n plus 1th term of this series would be minus 1 to the n times minus 1 times x to the 2n plus 2, plus 3. plus 3 over, and this would be 2n plus 3 factorial. But what I find to be easier is just writing 2n plus 1 factorial times 2n plus 2 times 2n plus 3, and then you must divide by this term, which is equivalent to multiplying by the reciprocal, so let's do that. So you must multiply times 2n plus 1 factorial over minus 1 to the n times x power 2n plus 1. Now we can see that a bunch of these terms are going to cancel out, like this and this and this and this. And in the end what we'll have is this is equal to the limit as n goes to infinity of x squared over 2n plus 2 times 2n plus 3. And we know that the ratio test, in order for the series to converge using the ratio test, this must be less than 1. So now, once we plug in the values for n to go to infinity, we see that this side is equal to 0. So the value of x has no impact on the convergence of the series. Therefore, the series will converge for all values of x, because no matter what finite value you give for x, it'll always be it'll always go to 0 because the n terms are going to infinity in the denominator. This means that the radius of convergence for this series is going to be equal to 0. That also means that the interval of convergence for this series is going to be minus infinity to infinity. Okay guys, I made a bit of a low IQ mistake in that one. Since the x term has no impact on the series, the radius is not going to be equal to 0, but instead it's going to be equal to infinity. Thank you. Hey guys, and welcome to another episode of Medium IQ Math with Akshay. Today we're going to be finding the power series of this function. G of x is equal to 1 over 1 plus x cubed. Finding the power series allows us to approximate a function with an infinite summation. So what you should remember whenever you make a power series is you always want to put it back into the form a1 over 1 minus r. So as you can see, this is pretty close to that form, but it's not quite there yet. We know that the a1 is going to be 1, but we need to take this 1 plus x cubed and put it into this form. So to do that, we just have to do 1 over, and then you have to do 1 minus, and then what would make this equal to this? You just have to make it minus x cubed. So now this function has been put into the form of a1 over 1 minus r, and it's going to be easy as cake to put this into the form of a power series. The general form of a power series is the summation of n equals 0 to infinity of Alicia, you can cut this out, right? Yeah, good. The general form of a power series is the summation of n equals 0 to infinity of a times r to the n power. Here we have our a term, which is 1, right? So you get 1 times r, which is negative x cubed, to the n power. So the power series notation of this function is going to be the summation of n equals 0 to infinity of minus x cubed to the nth term, to the nth power. And that's the answer.
UC exam. Taylor and Maclaurin series are really a large part of the series for the entire test. So let's just go over really quick what Taylor and Maclaurin series are. Taylor and Maclaurin series are a way to estimate a function, write it as a summation of an infinite series. And so you can do it using this general expansion. What's the difference between a Taylor and Maclaurin series? Well, a lot of students get this confused, so be careful. You should know that Maclaurin series are just a form of Taylor series. Taylor series are centered around a value a, but for Maclaurin series, they're just centered around 0. Let's look at an example of this. So our problem wants us to find the third degree Taylor polynomial for f of x equals 1 over x squared about x equals -1. Look out for this key term polynomial. What is the difference between a Taylor polynomial and series, you may ask? Well, a Taylor polynomial is just a part of the series. So the series is the general form for k, or the term approaching infinity, but a polynomial is just a part of that. So it says third degree. That's where students make their second error. When you write out the form of the expansion, you see that x has no degree here, a degree of 1 here, and a degree of 2 here, and so on. So when it says third degree, it's not looking for the first 3 terms, it's looking for where x has the degree of 3. So it will be more than just the first 3 terms, because if, as you can see, the third degree is actually the 4th term. So now this problem is asking us to find it about x equals -1. So for the leading coefficient of each x term, you want to find where this is where x is -1. So plugging in -1, we get, okay, now let's plug these into our equation. So the third degree polynomial for f of x equals x over 1 over x squared is actually equal to watch your negatives. And then you can simplify from here. But remember that in the calculus exam, they do not care about simplification. So if it's a free response question, then remember that you don't need to simplify. However, if you were given this problem with Maclaurin polynomial and it didn't give you about x, then you would just plug in 0 for the value of a. The next application of Taylor-Maclaurin polynomials that you'll see on the AP Calculus BC exam is with Lagrange error. So this problem is asking us to find the error if we were to calculate sine of 0.1 using the third degree polynomial. Well, we've had to memorize what sine of x, the Taylor polynomial form of it, is. So that is the third degree of this is equal to x minus x cubed over 3 factorial. Not too hard. But this is asking us, what is the difference between if you plug in 0.1 and if you were to actually calculate sine of 0.1? Well, good thing we have an equation to help us. Let's try to contextualize what this means in terms of our problem. So here, I just plugged in the third degree polynomial of sine of 0.1 into our equation to help us. So this is basically asking us to find the maximum value of the next degree value of sine and multiply it by this. So for the third degree polynomial, it would just be x to the 4 over 4 factorial, n plus 1 factorial. Now, how do we find this maximum value? Well, first, let's find what the f to the 3 plus 1, or the 4th derivative of sine is. Well, since sine is cyclic, the 4th degree derivative of sine is actually just sine. Now let's go to the max value. How do we find this? Well, over here, the Lagrange theorem states that 0 has to be less than c, less than x, or 0.1. So that also means that 0 has to be less than sine of c, the 4th derivative of c, of sine, has to be less than 1, because sine is always less than 1. So now let's plug this in into this Lagrange error formula. 1 times x to the 4 over 4 factorial. But wait! We know what x is. X is 0.1. So that means that the error is less than or equal to 0.1 to the 4 over 4 factorial, which is approximately 0.000004. So we just found the error of the third degree polynomial expansion of sine of 0.1 in comparison to the actual error of sine of 0.1. If